So in class we are also studying chapter 2.7. We're going to learn a little bit about functions and graphs. Our objectives are to test for symmetry, either around the y-axis or x-axis, identify even and odd functions, graph piecewise defined functions, investigate increasing, decreasing, and constant behavior of a function, and determine the relative minima and maximum of a function. The first objective is to test for symmetry. Consider an equation in the variables x and y. Symmetric with respect to the y-axis is by substituting a negative x for x results in an equivalent equation. Symmetric with respect to the x-axis is substituting a minus y for y results in an equivalent equation. And symmetric with respect to the origin is substituting x for x and a negative y for y, and the results are equivalent for both equations. From a graphic perspective, we have symmetric for the y-axis, something like a parabola that is a mirror image of each other around a y-axis, or symmetric with the x-axis, where we have a parabola on its side with a square root function, for example. Symmetric with respect to the origin is something like x cubed, where it can be rotated directly around in a 180 degrees, and it turns out to be the same function. So now we're going to determine whether the graph of an equation is symmetric to the x-axis, the y-axis, origin, or none of these. So in our first example, we have y equals x cubed. So here we look at the y-axis and we substitute in a negative x into the function. When we do that, we have y is equal to a negative x cubed, but y has to equal x cubed, positive. So no, it is not symmetric around the y-axis. For x-axis, we have a negative y is equal to x cubed. Well, this implies that y is equal to a negative x cubed, but y has to equal x cubed. No, it's not symmetric around the x-axis. Finally, we have the origin, where we have a negative y and a negative x in the function negative x in the function. This is equal to a negative y is equal to a negative x cubed, but now we can multiply through by a negative 1, and so y is equal to x cubed. And yes, that is what our original function is. So, guess what? It is symmetric around the origin, which is not surprising since graphically it is a snake that goes through the origin, and if you rotate it 180 degrees, it is symmetric about the origin. Now we're going to try the next equation. So in the second result, we see for the y-axis we have y is equal to a negative x squared plus 5. When we solve for the negative x part in the function, we see that y equals x squared plus 5. So this is our original function. So guess what? It is symmetric about the y-axis. That makes sense because it is a parabola. And so the next two show that, in fact, they are not symmetric around the x-axis or the origin. Once you find which of the three that is symmetric to, it cannot be symmetric to the other two. So all you have to do is find the one that says yes, and that's the one to go for. So now I want you to look at the third one, which is x squared plus y plus 1 squared is equal to 4. I would like you to try that on your own and see whether you find that it's symmetric to the x-axis, to the y-axis, or to the origin. So in this result, it is symmetric about the y-axis. So in this particular case, I rewrote the equation of the circle such that I solve for y, and I would use that also on my calculator. So it's y is equal to a negative 1 plus or minus the square root of 4 minus x squared. So to find out if it's symmetric about the y-axis, I put in a negative x, and when I do that, I see that I get, and I see a slight mistake here. It should be a negative x squared, but in any event, I get y is equal to a minus 1 plus or minus the square root of 4 minus x squared, which in a sense is the original equation. So it is symmetric about the y-axis. Interestingly enough, we know the center is at 0, 1. And that means that the diameter is along the y-axis, which means that it's symmetrical about the circle is symmetric about the y-axis. Now I would like you to try the very last problem. So for our very last problem, we have an absolute value. Absolute values in parabolas are basically the same idea in that they are all symmetrical about the y-axis if they start at the origin or near the origin. In this particular case, the vertex is at 0, minus 2. But anyway, we will go ahead and use this idea. Y is equal to the absolute value of negative x minus 2. And when we take the absolute value of a negative x, we get just x, the absolute value of x minus 2. So it's the original equation, and yes, it is indeed symmetrical about the y-axis. So we know we don't have to do anything more than that. Our next objective is to discover what are even and odd functions. An even function is where when we replace a negative x into the function, we just get the same function back for all x in the domain of f. That is, it's symmetric to the y-axis. In fact, it's just like the reflection problem that we had, symmetric to the y-axis. For odd functions, we have the issue where we have a negative x that is put into the function is equal to the negative of the function for all x of the domain. This is symmetric to the origin. So in this example, we're going to find out whether a function is even, odd, or neither. So we're going to do the first one, and we will show you how that's done. So in our first example, f of x, x to the fourth minus x squared plus 2, we put in a negative x into the function and evaluate. When we do that, we have a negative x to the fourth minus a negative x to the second power plus 2. When we evaluate that for an even power, we just get x to the fourth minus x squared plus 2, and that's the original function. So f of minus x equals f of x. That's an even function. Now I would like you to try the next one. F of x is equal to x cubed minus x plus 3. Pause the video and try it. So now we try this. We have f of minus x is equal to a negative x cubed minus a minus x plus 3. That gives us, for a function that's with a negative x, is equal to a negative x cubed plus x plus 3. So we notice that the function evaluated at a negative x does not equal the original function. It's not even. Now we will do the odd part. A negative f of x is just the negative x cubed minus x minus 3. We just multiply through by the negative sign. We see that a negative f of x is not equal to the negative x evaluated at the function, so it's not odd. Now we have the last function for you to evaluate. F of x is equal to x cubed minus x. Please pause and see if you can do this one. So for our last function, we have f of minus x evaluated at minus x. So we have a negative x cubed minus a minus x. We see that when we get it to evaluate, we have a f minus x is equal to a negative x cubed plus x. Well, this means that, guess what? F of minus x doesn't equal the original function, so it's not even. Now let's try the negative f of x. So we multiply through the function by a negative 1, and we see we have a negative x cubed plus x. Well, in this case, the negative f of x is equal to the negative x evaluated. So it is an odd function in this particular case. These functions can also be graphed to see whether or not they're even, odd, or neither. And if again they're symmetric about the y-axis, then they're even. If they're symmetric about the origin, they're odd. So here's the example, our graphic examples, to determine if a function is odd, even, or neither. In our first example, where we have the first graph, we see that it's symmetric about the y-axis. That means this is an even function. In our second graph, we see that if we are able to rotate the graph 180 degrees, we end up with the same graph around the origin. Therefore, this is an odd function. Our third objective is to look at piecewise functions. So in our first function, where we have f of x is equal to x squared plus 1 when x is less than 0, or x minus 1 when x is greater than 0, we will first evaluate it at different points. So when f is a minus 1, we notice that it's less than 0. So we would use the first function. We would put minus 1 into the x squared plus 1, and we get 2 in this particular case, because a negative 1 squared plus 1 is 2. For f of 0, we say, well, where is 0 in this particular domain? Well, x is greater than or equal to 0. We use the bottom function, x minus 1, so we put 0 in there, and we get a minus 1. And so now we have f of 5, so we look at 5 and it's greater than or equal to 0, so we use the bottom function. 5 minus 1 is 4. So now we come over to our graph and we see how this graph works. For the point at 0, we have a discontinuity where when x is equal to 0, it has to be at a minus 1. But we can still evaluate the other function at 0. We just have to use an open end circle at that point. So when we put 0 in the top function of x squared plus 1, we get 1, but it has to be an open end because, why? It is a function. And a function can only be evaluated at one point along for a particular y value. So now this function, the top function, x squared plus 1, is a parabola, and it's only parabola for the values of x that is negative. And you can see that that's how that graph works. On the other side, when x is greater than 0, it's just a line. And now we have this line in that fashion. So what I'd like you to do is we have another function, h of x, and I would like you to try this function. And I would also like you to graph it. And this time, I see I've got the wrong graph here. We need to change the graph a little bit. So we're going to make it every 2 points. This is a negative 10, not a 5 here. So this is no longer 5. This is at 10. And the bottom is a negative 10 here. So each unit is 2. And so I would like you to try this. You'll evaluate first, and then you'll try to graph the equation. So you should have gotten the following numbers. For h1 you should have gotten 4. For h3 you should have gotten 7. For h4 you should have gotten 7. And for h5 you should have gotten 9. And now when we graph this particular function, we look at where x is 2, and we see that when x is 2 or less than 2, we go to 2, this function is at 7. So we go 2, 4, 6, 7 is probably about right here. And now when x is 0, we have 3. So in this case we have this function going down to here, and then from here it will go back up because it will be positive as it becomes more negative. So when it's 1, it's 4, and so forth. And so this function will look like this from this point. Now from 2 to 4, it's at 7, so we'll have a function that goes from here to here. And then it's a straight line because at 4 it's still at 7, but now when it's 5, it's 10 minus 1, which is 9, which is about, so when it's 9, it's about right here. Let's see, 9 and 9 is about right here. So this line goes like this. So there's our function. So here we have some additional functions to graph. Here are piecewise functions. We'll do the first one. F of x is 1/2 x plus 1, and that's evaluated for x less than 2. And then we have minus x minus 1 for x greater than 2. So our turning point is at 2. And so we'll go ahead and we'll do some of the graphing on this one. What I normally do is I will go ahead and create a table real quickly and show you how that's done. So I created the first table for x values. You'll notice I have some 2's here that are very important in our graph. So in some ways we start out where the point is going to be a disconnect. So here we have 2 for the bottom, where 2 is actually equal and it has a connection to it at minus 3. So at 2 we have a minus 3 here. And then we also have at 2 where the connection is, we also have it at 2. So we have a 2 at 2. So in this particular case, we have an open end at 2. And I'll put an open circle at 2. So now we look at x going in the negative direction. When x goes into the negative direction and it's a line, we have an we have a y-intercept or actually we have the x-intercept and the y-intercept in this particular case. We have the y-intercept when x is equal to 0. When x is equal to 0, we are at y is equal to 1. And the x-intercept is when we have a negative 2, we have it at 0. Right? So we have a line going in this direction. And now for the other one, when x is positive, we have a 4, and we know that it's at a minus 5. So we can go over 4, and we can go to a minus 5, which is down here. And so this line starts going in this direction. There's our graph for the first one. I'd like you to try the second one. The second one's also very interesting, and I'd like you to try that one. So I went ahead and drew up the x and y axes, or the numbers for the x and y's, and now we will put the points in where they should be. So when x is 0, we have a minus 1 in both cases. So we start off with a minus 1 at 0. Now from there, if x is negative, it just stays at a negative 1. So we have a constant of that function. Now we go to the interval between 0 and 2, and we're on this line. So now we know when x is 1, we're at 0. When x is at 2, we're at 1. And those are all connected lines. So it goes all the way up to here. Now, when x gets above 2, we have a disconnect here. So when x is 2 at the disconnect, we have 4. So now we go up 1, 2, 3, 4. And now I have an open-ended circle. Or actually, when x is 2, we also have 2, actually, because when we put a 2 in, we get a negative 4 plus 6. So we have a 2, and it's an open-ended circle at 2. And now we'll go in the opposite direction. When x is 3, right, we have a negative 6 plus 6, which is 0. And then when x is 4, we have a negative 8 plus 6, which is a negative 2. So now we're down here at negative 2. So now we have a line going from here down to here. And these lines don't touch, by the way. I think I made a slight error here, so let me redo this just a little bit to make it a little bit clear. We're at here, and we're going down this way. But now we're going, there we go. And this is an open-ended circle right here. So there we go. There's our function. So here's an application for a piecewise function. A new job offer in sales promises a base salary of $3,000 a month. Once the salesperson reaches $50,000 in total sales, he earns his base salary plus a 4.3% commission on all sales of $50,000 or more. Write a piecewise defined function in dollars to model the expected total monthly salary as a function of the amount of sales X. So here's our function. S of X is equal to 3,000 when x is less than 50,000, and 3,000 plus 0.043 of x when x is greater than 50,000. In this section, we're also looking at Objective 4, intervals of increasing and decreasing constant behavior. So, for increasing functions, we notice that if x2 is greater than x1, and if f of x2 is greater than f of x1, then we have an increasing function. If x2 is greater than x1, but f of x1 is greater than f of x2, we have a decreasing function. In other words, as x increases, y is decreasing. And finally, if x and 1 are on the same interval, and we have f of x1 is equal to f of x2, we have what's called a constant function. So when we look at increasing and decreasing functions, we're only interested in the domain part of the function when we are writing it in interval notation. So for example, the first function in f of x, we see that our function is actually increasing from this point to this point. Why? Because as x is increasing, y is increasing. So we know that that part we have from a negative infinity to 2, it's increasing. And then we also have another increasing part. From this part, it's increasing. As x is increasing, y is increasing. So, from 2, infinity, right, it's also increasing. And we could use brackets in this case for the 2's. It doesn't make any difference because they're actually connecting up. For decreasing functions, we see only one piece where it's decreasing. It's right here. It's decreasing from 0 to 2, right? As x is increasing, we see that in fact y is decreasing. So in this case, it's from 0, to 2. And finally, we see a constant part. The constant part is right here, right? The constant part is right here from, it looks like -2 to 0. Okay, I'd like you to pause and see if you can do the next function graphically. So in this case, I look at this whole function and we see what? We see that it is decreasing. As x is increasing, y is decreasing. So in this case, we don't have anything that's increasing. We have everything decreasing. Always, really, in this case. Right? And constant is none. Right? So objective 6 is to look at relative minimum and relative maximum values for functions. In this case, when we see a sort of bump in the road as far as our functions are concerned, we see hills and valleys. Those are called local relative maximums and minimums, and they occur within a certain interval period of maximums and minimums. So we're going to identify local minimums and maximums of functions. So in our first example, we see a function and it says we're going to identify the lowest point in this function, and in this case the lowest relative minimum is here. That's the lowest relative minimum. that point is at -2, is the lowest point. Well, actually, in this case, I'm sorry, the point itself for y actually is at a -1, right? The lowest point relatively is a -1, is the lowest point in a small interval surrounding x equals -2, right? At x equals -2, right, the function has a relative minimum of a -1. That's what we would say. So this is what we would actually say. At x is -2, the function has a relative minimum of a -1. So now we'll look at the next one, and we say the point, right here, the point 1 is the highest point in a small interval surrounding x equals 0, right? So at x equals 0, the function has a relative maximum of 1. So now in this example, we're going to identify the location of any relative maxima or minima of the function. So at this particular case, we want to find a minimum. So x is a minimum or a relative minimum at -1. So at -1, the function has a relative minimum of a -2. Here it is. There's our relative minimum, right? So x, and there's another minimum actually, at x is equal to 1, 2, 3, 4, at x at 4, right, we have a relative minimum of 0. There's our other minimum value. And finally, at x at 2, right, at x at 2, here's our relative maximum. And the relative maximum is at 3. So in this last function, we want to identify the location and value of any relative maximum or minimum in the function. In this case, we don't see, there's no max or minimum or min, right? No max or min. But guess what? There's an inflection point. This inflection point is at 0, 0. It's where the function is changing from it's accelerating, and then it kind of levels off, and then it re-accelerates. They call that an inflection point. Well, that concludes our chapter 2.7. Please look at problems in the book and complete your assignment and then the quiz.